Okay, a 500 turns of solenoid is 8 centimeter long. When the current in the solenoid is increased from 0 to 2.5 ampere in 0.35 seconds, the magnitude of the induced EMF is 0.012 volt. Calculate the inductance of the solenoid, cross-sectional area of solenoid, the final magnetic flux linkage through the solenoid. Okay, so I want to ask you, this question is about inductance. We need to first identify what kind of question is this, yeah? About what topic? So I saw about inductance. Okay, so this is either self-inductance or mutual inductance. Self or mutual induction, yeah, about self-induction or mutual induction. But is it self or is it mutual? Is this about self or is it about mutual induction? Self means only involve. Okay, sorry. Self means only involve one coil. If mutual means it involves two coils. So look at these questions. How many coil it involve? We talk about solenoid. First, we talk about solenoid, and then is there any other coil or solenoid involved? 500 turns of solenoid, and then the current in this solenoid, induced EMF in this solenoid also, yeah. There's no other coil or no other solenoid. There's no second solenoid, there's no second coil, isn't it? So all along is just one solenoid. So it's not about mutual. It's not about mutual. It's about self only. Okay, it's about self-induction because only have one coil or one solenoid. It's about self-induction. So this inductance is the symbol. Is the symbol L. It's not the M. It's not the mutual induction. It's not the mutual induction. It's the symbol L only. Yeah, it's about self-induction. It's not mutual induction because only involve the one solenoid. There's no two solenoid. Okay, only one solenoid. Yeah, no two coil, just one coil. Okay, so now, okay, what information given? We have the number of turns of solenoid. Okay, just this is the N, capital N. This is the length of the solenoid. And he said the current in the solenoid is increased from 0 to 2.5 ampere in 0.35 seconds. So what is this value? So this is about the current. So this is the initial current and this is the final current. Yeah, it increased from 0 to 2.5. And this is the time taken. 0.35 seconds is the delta T. Yeah, time taken. And then this induced EMF. This is the magnet. Okay, so this is the induced EMF. All right, magnitude of induced EMF. Okay, induced EMF. The induced EMF by self-induction. Okay, so we want to find the L. Yeah, the value of L. Okay, so we want to find the self-inductance. Okay, how to find? Okay, this is about self-induction because only involve one solenoid. There's no second coil. Okay, only involve one solenoid. So what formula do you have under self-induction? If you look at my notes, okay, this is my notes. Yeah, important equations for self and mutual inductions. Okay, so if you look carefully, this one is E, right? Self-induction, we have E equal to negative N d phi over dt, or E equal to negative L di over dt. Okay, Li equal to N phi, L equal to mu naught N square A over L. If mutual induction is almost the same, you see, almost the same, just the L we change to M. Just L change to M. But the formula is almost the same. this one n square instead of n square because we are using 2 coil. Yeah, we are using 2 coil. So instead of just 1 coil, this one is just 1 coil, but you use this n square. Instead of n square, you put n1 and 2 because this one only have 1 coil, this one has 2 coil. So take the number of turns for both coils. See, n1 and n2. This one is just to take the number of turns for the same coil, for the 1 coil. So take it double. Take the same coil twice. So n square. It's actually this one is m times n times n. Or we can say n1 n1. This one is n1 n1 because only 1 coil. So n1 n1. This one is 2 coils, so it's n1 n2. Okay. So but it's, overall you can see the formula is almost the same. Just the L change to M, and then this one n square change to n1 n2. Remember this is a summary. I can say this is, okay, I think can write down this this as your notes. Okay, write down this in your notes. This is the summary for self-induction and mutual induction, and it's very helpful formula. Okay, write down this one in your notes. You will use this, you will find this very useful in problem solving. Okay, so right now is self-induction, just this formula. Yeah. Okay, so okay, let me write down my formula over here. So self-induction, I have E equal to negative and d phi. Okay, hold on a second. And d phi over dt, and then we also have negative L di over dt. And then because these two equal to each other, you see, because both of negative n d phi over dt equal to E, this one negative L di dt also equal to E, so they are equal to each other. So I can say that negative n d flux over dt equal to negative L di over dt. So I can cancel the negative. Excuse me. The dt also I can cancel. So I got, lastly I got what? I got n phi equal to Li. Okay, and phi equal to Li. That is this one lah. Li equal to n phi. Yeah, the same as this one. Okay, actually this n phi is the magnetic flux linkage. You know that. This one is the this one is just the magnetic. This one is magnetic flux. Okay. But we know that this n times phi is the magnetic flux linkage. So we can change the formula into this one. Magnetic flux linkage equal to Li. This one is magnetic flux linkage. This one is magnetic flux linkage. Understand? Okay. Magnetic flux linkage n phi, because we know that magnetic flux linkage is n times phi. Okay. This is just for the small phi is just for 1 turn. This one is many turns, n turns. Understand? Flux linkage means have many turns. Small phi means have only 1 turn. Okay, so this one can be substituted by magnetic flux linkage. So magnetic flux linkage equal to Li. And then some more I can further elaborate. I can further elaborate the L. Lastly, I have the formula. What? I have the formula. This L is mu naught. 1 second. Is mu naught n square A over L. Over L. So which is this one lah. Okay, mu naught n square A over L. Alright. Okay, so I have this formula, which is an important formula. I just want to write it down. So I have 1, 2, which I always use, 2, 3 formula, and 4 formula. These 3 formula, yeah, which I'm going to use. So normally it's this one, this one, this one, and this one. Okay, this one also can lah. Yeah, this one is the same as this one. Okay, So now okay, want to put a shape. Excuse me. Just want to yep. Oh, I like this. Okay. All right. Okay, I'm going to use all this formula to solve the questions. Now for question A, I want to do the question A. So I'm going to do the question A. Question A. Inductance. I want to find the inductance L. So I can use which formula? I can use I have the induced EMF, right? E induced, I have the initial current, final current, the change of time. I can use the second formula. So E induced equal to negative L di over dt. So if you look carefully, this di is change of time. Change of time is like I final minus I initial. I final minus I initial. This is delta t. Okay. So all right. So okay. So let's find out. Okay. So okay. E induced I also have. I also have. Okay. Later on I substitute. I will. Okay. Next I want to find the L. So I final is 2.5, and then initial is 0, and then change of time is 0.35. 0.35 second. Okay, this one is ampere in SI unit. So I want to find L. I have the E induced 0.012, but this is just the magnitude. See that? This one is the magnitude only. So you need to give direction for this E induced. So this E induced is actually is not 0.012. Okay. This E induced is actually 0.012. Actually, in front got a negative sign. In front there is a negative sign because it's back EMF. It's back EMF. Yeah. Okay, it's back EMF. So it should have a negative sign. It should have a negative sign. Instead of just putting 0.012, you should put a negative. You should put a negative sign there. Okay, so 0.012 volt. All right, because okay, why do we put a negative sign here? Because later on when we calculate L, we don't want the L has a negative sign. Okay, you see, yeah, calculate first and then you see. Okay, so let's calculate. Multiply 0.35 divide by 2.5. So the answer is so L inductance is L must be positive lah. L must be positive value. It's a constant value. Because it's a constant value. Okay, unit is Henry. Self-inductance unit is Henry. It must be positive value. Understand? It must be positive. So is the answer correct? Yes, that's correct. Okay, that's correct. Okay. So you should put a negative sign here. Actually, you should put a negative sign here. Okay. Should put a negative sign here. So so you should put a negative sign. So negative and negative. Because why you have negative means because it's back EMF. Back EMF. It opposes the change. You know, because the current is increased. Current is increased. The current increasing. So the delta I is a positive value. Yeah, current increasing. So to oppose the change, it produces an opposite direction voltage. To decrease back the current. So the negative is just the direction lah. Yeah, it's just about direction. The negative sign is just about direction. It's all because of Lenz's law. Yeah, Lenz's law. Okay. Put a negative sign there. Okay, so negative. So the L should have a positive value. L should put a positive value. It should become a positive value. L shouldn't be a negative value. Okay, so and then question B. Yeah, let's look at question B. I want to find the cross-sectional area. I want to find the area of the solenoid. So how going to do that? Question B. Cross-sectional area. I think you can use a formula. This one. L equal to mu naught n square A over L. Just use that one. So L equal to mu naught n square area over L. L already have 1.68 exponent negative 3 Henry, and then mu naught you can find from list of constant. Let me get the list of constant. Do I have the list of constant? Yes, I have the list of constant. Mu naught is list of constant provided have the value of mu naught 4 pi exponent negative 7. Okay, 4 pi exponent negative 7. Okay, 4 pi exponent negative 7. Okay, that's right. And then n square, what's the number of turns? Number of turns is 500 turns. 500 turns. Don't forget the square. Yeah, many students forget about the square. And area, and then the total length divided by the total length. What's the total length? Total length is 8 centimeter long. Centimeter change to meter, so divide by 100. So it's 0.08. 0.08 meter. 0.08 meter. Okay. Okay, so A. So let's calculate. So 1.68 exponent negative 3 times 0.08, and then divide by this 4 pi exponent negative 7, and then divide again by this 500 square. So the answer is this one, 4.278 exponent negative 4 meter square. Yeah, is that answer correct? Is the answer correct? Yes, that's correct. Yeah, 4.28, 4.28, 4.28. Yeah, 4.278 exponent negative 4 meter square. Change to meter already. Yeah, that's correct. My answer is correct. Okay. Now, finally, what's the final magnetic flux linkage? Linkage. You see that? Linkage means the capital phi lah. Capital phi, which is number of turns multiply small phi. Small phi is magnetic flux for one area. Linkage is many areas, many turns. Okay, so how to find the phi? Use the third formula, which is this one. Magnetic flux linkage equal to Li. Okay, so question C. Let's do question C. Question C. So magnetic flux linkage is equal to Li. So L linkage, remember, is the capital phi, not the small phi, is capital phi. So L is, I got the L just now, 1.68. 1.68 exponent negative 3. And then current, what's the current? What's the current? Do I have the current? Oh, I don't have the current. I have the current. Yeah, you want the final, isn't it? The final. Okay, here there is a word. I want the final. So the final. I want the final lah. The final flux, final magnetic flux linkage. So this one is final. So the current also use the final lah. Okay, final magnetic flux linkage. So the current also final. The final current is what? Final current is what is this? The final current is 2.5. 2.5 ampere. That's the final current, 2.5. Okay, put in the 2.5 value. So 2.5 ampere. So okay. So what do you get? 1.68 exponent negative 3. 1.68 exponent negative 3 multiply 2.5. So I got the answer is 4.2 exponent 4.2 exponent negative 3 verbal. That's the unit for magnetic flux. Verbal is the unit for magnetic flux. Okay, 4.2 x. If the unit for flux is verbal, if L inductance is Henry, understand? Henry. Okay. Okay. So is the answer correct? Is the answer correct? Yes, it's 4.2. 4.2 exponent negative 3 verbal. Okay, that's correct. That's the answer. Okay, so I think that's all for this question. So okay, see you in the next video. Bye.